Alright, first thing I'm going to do is go over the review for the first half of Chapter 3 and mention the things that you need to know for the test. Chapter 3 is basically just your first application of derivatives and what they mean graphically. So I'm going to skip right to the review. Alright, there's not so much of a review here as there is kind of a compilation of all the different parts that we've talked about. So that's what I'm going to run through. Just lesson 3.6 and do one or two of the questions at the end. So summary of curve sketching. If you decided to make a list of the most important topics in all of your previous math courses, it is likely that everyone would mention graphing. Graphing shows up in every math class. It is consistently significant. It is a consistently significant part to nearly every lesson. It allows us to verify results, analyze different aspects of the problem with ease, and up until this point, the only graphs you had to create were able to be copied by using the calculator's table capabilities. The graphs that we have today, some of those numbers will be on the table, but we're going to figure out how to create the essence of the graph without worrying about all the different points to be graphed individually. We could analyze the information, but we did not personally produce the graph. That changes now. But before we reach the peak of the first part of the chapter, let's review a few items that will make curve sketching process more meaningful. Some of these things you could find in Chapter P, the pre-calculus chapter. Again, not to be confused with pre-calculus because they're very different, but just things that happen before calculus. If you were to find x-intercepts, the strategy would be to plug 0 in for y. If you plug 0 in for y, you're getting rid of y, leaving just the x. So on the opposite end of that, we're going to plug 0 in for x. You may be able to hear my son in the background, but hopefully my husband will maybe get his pacifier. Alright, moving on. If you're trying to test for symmetry, with respect to the x-axis, again, just like before, we're doing the opposite. So we're going to plug negative y in for y and compare. Meaning, if you have an equation that has x's and y's in it, replace all of your y's with negative y. If the result is identical to the original, then we have symmetry with respect to the x-axis. Think about that. Symmetry with respect to the x-axis might look something like this. That means your y and your negative y, these would have to be the same number, but one positive, one negative, have the same x value. So both regular y and negative y should come out to be the same as the original equation. For symmetry with respect to the y-axis, we're going to plug in negative x in for x and compare. So a quick sketch of what that might look like, just a standard parabola. It's a good way to start. This point has a match over here. They have the same y value, but if I plug in negative x or positive x, I should get the same value. I should get something that is equivalent. For something to be symmetric with respect to the origin, you'd have to do both. Plug negative y in for y, negative x in for x, and compare. Quick sketch of that. I know that the cubic function, the basic cubic function, the mother or the parent cubic function, is symmetric with respect to the origin. That means I can twist it 180 degrees and it looks the same. If I have the point xy, I should have a match at the negative x, negative y, meaning if I plug negative x, negative y into this, I should end up in its symmetric over the origin position. Okay? Domain and range. When it comes to conflicts with the domain, there's two that stick out to me. You can't have 0 in the denominator. So if you have a fraction, you have to eliminate anything that's going to create 0 in the denominator. If it says x minus 3 in the denominator, then it's all real numbers except 3. Another problem would be you can't have negative, let me think of what it's called, square root, radicands. I don't know why I started with an I. I was going to write discriminant, but the discriminant is very specific to the quadratic formula. Radicands are anything that's inside of the radical. Now, you could use negative numbers before in previous courses, but because calculus is the study of real numbers, we are not going to have anything that's negative inside that square root. All of these need to be restricted to have appropriate domains for the question. The range is most easily found, at least in my opinion, by looking at the graph. If you have a graph in front of you, then you can see what y values exist, what y values are being used, and that's how I usually determine my range. Where might there be discontinuity? Well, we know of two different types of discontinuity that we've spoken about already. We've got removable points of discontinuity, and those exist when you have 0 over 0. Another word for removable is whole. We've also talked about non-removable points of discontinuity. Most commonly, if you have a non-zero number over 0, then you end up with an asymptote. These break up your graphs. You may also have other points of, or other areas of discontinuity, but those are the two that we're going to stick to right now. Speaking of discontinuity, when we have vertical asymptotes, the way that you determine that is by setting the denominator equal to 0. I'm going to make a little note. The numerator is not 0. So if I set the denominator equal to 0 and I get a number like 2, but 2 also makes the numerator 0, it's not a vertical asymptote, it would be a whole. So we would not use that for this, but it would still be some sort of discontinuity. What do the first and second derivatives determine? So we're at differentiability now, chapter 2 information. First derivatives determine whether the function is increasing, decreasing, or turning. Now, if it doesn't fit into either of those three categories or any of those three categories, then it must not have been a differentiable number. Our second derivative tells us whether something is concave up, concave down, or a point of inflection. That's just where we change from one to the other. Concave up would have a positive second derivative. Concave down would have a negative second derivative. A point of inflection would be your second derivative equal to 0. Second derivative greater than 0. Second derivative less than 0. This is your second derivative equal to 0. This is your first derivative greater than 0. Remember, first derivative is your well, when you plug in a number for the first derivative, you get your slope. So it would make sense that if it was a positive number, it'd be a positive slope. First derivative less than 0 means decreasing, and if it's a turning point, that's when your first derivative is equal to 0. In other words, your slope is flat, horizontal, so you must be turning at that point. Relative extrema. Now, your turning points, where your first derivative is equal to 0, this is your extrema, but how do you know if it is relative or if it's absolute? You have to compare. Compare to the endpoints. By finding the respective y's. So when you take the derivative and you set it to 0, you're going to get a bunch of critical numbers, or maybe just one critical number, or maybe no critical numbers. But those critical numbers are x values that allow for turning points, or that create turning points, or that exist at turning points, whatever the terminology, it doesn't matter. Oh, terrible graph, sorry. So here's a turning point. I need to make this a little bit more obvious. Here's a turning point. Here's a turning point, okay? Each of those would have a derivative equal to 0. But let's say that I stopped this graph and I looked just at this window right here, okay? Which means I stopped it here, I stopped it here. How do I know if this is a relative or an absolute minimum? Well, it's going to be an absolute minimum just because it's the minimum of the two minimums that I found, minima, but also this is an even degree function, same end behavior, so I'm never going to come back down from these two arrows. This one right here, this maximum, would be a relative maximum because in comparison to this endpoint, that would be an absolute maximum on this interval. If I didn't include the interval, if I let the graph go on toward infinity, then nothing here would be absolute except this one. Everything else would be relatively min or max. Hopefully that makes sense. What types of concavity exist and how are they found? We said this already. We have second derivative greater than 0 is concave up. You might see something that looks like this. Basically, if you're able to, the way I describe it in class, hold water. Obviously, you don't want a cup that looks like that, but if it can hold water, it would be considered concave up. If the second derivative is less than 0, that's considered concave down. On the other hand, that's a graph that might look like this, where if you try to put something in it, it's going to slide right off. So it's bending with this side in mind. If by chance you get a second derivative equal to 0, that's not talking about concavity, that's changing concavity. That would be a point of inflection. And you would see both concave up and concave down, but the order of those two doesn't matter. There's a spot somewhere right here where this side is up and this side is down. And when you change from one to the other, that's a point of inflection. So it goes on to say, where will you find a point of inflection? Again, it's where your second derivative is equal to 0 and is differentiable. And you know, there's other things. Everything's not just so cut and dry, but at least that's a start of how to figure it out. Set your second derivative equal to 0 and solve and see what happens. Horizontal asymptotes are found when you take the limit of the function as x approaches either positive or negative infinity. Notice this plus and minus is on the left side, so this is talking about two different limits. If it was on the right side, it'd be saying we'd be coming from the left or from the right. Your three conclusions are, if it's top heavy, meaning your exponent of the numerator is larger than the exponent of the denominator, then your answer is going to be either positive or negative infinity for a limit. If it's bottom heavy, meaning the degree of your denominator is larger than your numerator, it's going to approach 0. And if the degrees, I won't even say degrees alone, I have to say leading degrees. We're talking about the degrees of each of the first terms. If the leading degrees are equivalent, are equal, then the horizontal asymptote is at the ratio of leading coefficients. So if I have something like x cubed on the top, x cubed on the bottom, and the coefficient of the top is 4, the coefficient of the bottom is 5, then my horizontal asymptote is going to approach 4/5. What must be true for the existence of an infinite limit? To be perfectly honest, I don't remember what I wanted to put here. How might you find the existence of an oblique asymptote? Okay, this is important. If you have a fraction, a polynomial fraction, polynomial in the top, polynomial in the bottom, a rational expression, if you will. You'll take the top, you'll divide by the bottom, and what ends up here without the remainder is the equation for the function, or is the equation for the graph of the oblique asymptote. So if this came out to be x plus 5 and then there was a remainder of 2, you would draw the graph of y equals x plus 5, and it would act as an oblique asymptote. An oblique asymptote looks like this. So you've got vertical asymptotes, you've got horizontal asymptotes, obliques are slanted, and you might see something that looks like this. It gets really close on that side and maybe looks like this on this side. This one has another asymptote right here. You can see just the way that the graph bends, but I wasn't concerned about that right here. All right, so here's your practice for the exam. Analyze and sketch the graph of y equals negative x squared minus 4x minus 7 over x plus 3. The fact that it is a rational expression means that I better check at some point the oblique asymptote. I'll do that in my asymptotes section. First thing I'm going to do is start with my basics. What are my intercepts? All right, I'm going to plug in 0 everywhere I have an x. Notice where I have the x is where I put parentheses and the number 0. This is 0, this is 0, negative 7 over 3. All right, so I have one intercept on the y-axis at negative 7/3. On the x-axis, plug in 0 for y. 0 is only the answer to a division problem if the numerator is equal to 0, because it has to be 0 over something to equal 0, and this can't be 0 for that to work. So I'm going to cross multiply, and that's going to go away. And I don't know about you, but I hate this negative, so I'm just going to divide it out and divide both sides by the negative. It's equivalent to this here. Again, just imagine me pulling the negative out. And then dividing both sides by that negative. This is not factorable that I know of, so what I'm going to do is the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. X equals negative b. So negative 4 plus or minus the square root of 16 minus 28. All right, I can stop here because I know that this radicand, or in this case it is a discriminant, is negative. It's going to be negative 12. Whoops, not discriminator. What? Discriminant. That's what happens when I try to multitask. Because that's going to be negative, I can stop negative 12 because we only work with real numbers here. So if this does not work out, then what I can conclude is that there is no x-intercept. In other words, there's no roots. Okay? What else in the pre-calculus chapter can I do on this page? Well, I can check for symmetry. If I plug in, I'll plug in negative x first. Negative x squared is positive x squared, right? Negative 5 times negative 5 would be 25. But this negative in front gets applied after, according to PEMDAS. Negative 4 and negative x is a positive 4x. Now I want you to imagine pulling this negative out of both the top and the bottom. Maybe the negatives cancel, but is this the original function? And the answer is no. All right, if it could be the original function, then we would have symmetry with respect to the y-axis. Now we plug in negative y. If I get rid of this negative, will this ever be the original now that I've introduced a negative that wasn't there before? And the answer is no. So I have no symmetry with respect to the y-axis. Now if I plug in negative y and negative x, I can bring this down. This becomes negative x squared plus 4x minus 7 all over. Well, if I bring this negative down here, that'll make that a positive x. I want you to imagine just this part right here. If I bring the negative out front, if I pull it out, then this is going to become negative. Either way, the two signs here are different. They will never be the same, and they're supposed to be the same. They're supposed to be x plus 3. So I have no symmetry with respect to the origin. Another thing you could do is just plug in a value if you wanted something that was a little bit more specific and less general. If I plugged in a value, if I plugged in 5 and negative 5, do I get the same answer? If I plug in 0, or that would be a bad one, 5 and negative 5 here, do I get the same answer? So keep in mind that that would also work. A counter example would prove that something is false. If it does come out to be the same thing, then I would ask that you try the general form to prove that it works for all of the points, not just those 2 points that you came up with. All right, what else can we find? We've got symmetry, we've got what did I just do? Intercepts. Domain. I'm going to do domain and range. I'll do domain right now. And I'll talk about asymptotes as well. So the domain. This was a fraction. My denominator was x plus 3. If I set that equal to 0, then my domain has to exclude the number negative 3. Therefore, my domain is all reals except negative 3. You could also say that your domain includes negative infinity to negative 3, not inclusive, and then negative 3 to infinity, since that's the only number that's not being used. Okay? Going with that goes hand in hand with vertical asymptotes. What does negative 3 do? Does it make my numerator also equal to 0? Well, the original fraction was negative x squared. Y equals negative x squared minus 4x minus 7 over x plus 3. Negative 3 makes the denominator 0, but if I plug in negative 3, I get 9. That makes it negative 9. Plus 12 would be positive 3. Minus 7 is negative 4. So the numerator and the denominator are different. The numerator is not 0. Therefore, there is an asymptote at the line x equals negative 3. It's not a whole. Horizontal asymptotes. When I take the limit as x approaches negative infinity of this function, what do I get? Well, it's top heavy, so I know it's going to be positive or negative infinity. Now, what's going to happen when I plug in a negative number? If I plug in a negative number here and square it, it's going to become positive, but this negative in front makes it negative. Therefore, that's negative. This is also negative. A negative over a negative would be a positive. If I plug in positive infinity, positive infinity squared would stay positive. Put a negative in front, becomes negative. This one was positive from plugging it in. A negative over a positive is a negative. All right, so we have opposite end behavior. What else can we check for? I just did our discontinuities. That's non-removable. Vertical asymptotes, I think we're basically up to the derivatives. And I leave those for the end because that's where the most work comes from. All right, I'm going to also throw in oblique asymptotes right here. Remember, this only is necessary when you have a fraction or a rational expression. I think I might have said radical before, and I didn't mean that. Rational. Negative x squared minus 4x minus 7 divided by x plus 3. X goes into negative x squared, negative x times, negative x and x multiplied make that number. So we're going to bring it down according to the algorithm and multiply it through. The next step in division is to subtract. So subtracting would change the signs. If I have a negative out front of this, it changes the sign. So you'll see the negative this time, but from here on out, I'm just going to change the signs. Negative x squared plus x squared cancels. 4x, negative 4x plus, if I distribute that, it becomes a plus, 3x is negative x. Bring down the negative 7. What do I need to multiply this by to get this? The answer is negative 1. Distribute that through. And remember, I'm not going to just write negative anymore. I'm just going to change the signs. Both signs. Okay, this remainder has nothing to do with the oblique asymptote. I have an oblique asymptote at y equals negative x minus 1. So when I graph this function, I'm going to make sure that I graph these two asymptotes very clearly, this vertical asymptote and this oblique asymptote, which again only exists in rational expressions or rational functions. All right, first derivative. It's denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. I'm going to simplify what I have so that I can actually solve it here. We've got negative 2x squared minus 4x minus 6x minus 12 plus x squared plus 4x plus 7. My numerator becomes negative x squared minus 6x minus 5 over x plus 3. The numerator factors. Can you think of numbers that multiply to 5 and add to 6? Multiply to 5 and add to 6, and the answer is 1 and 5. All right, so if I set this equal to 0, remember only the numerator will matter because the denominator will go away once I cross multiply. Therefore, my critical numbers are negative 1 and negative 5. These are the two numbers that make my numerator equal to 0. My second derivative, I'm just going to do it from what I ended up with here. It's denominator times the derivative of the numerator. Actually, I'll do it back here. That seems to be a little bit easier. Negative 2x minus 6 minus the numerator times the derivative of the denominator all over the denominator squared. Now look very carefully at this answer. I have plus 3 in the first section, in the second section, and in the denominator. I want you to imagine factoring out x plus 3 from the two top sections and from the bottom. This product, I can eliminate one of the x plus 3's, I can eliminate the x plus 3 from this product, and I can eliminate one of them down here. Now it's squared, but I forgot to square it from there, so this should technically be a 4. But now it's a 3. And I'm going to simplify what I have left over. Negative 2x squared minus 6x minus 6x minus 18. Positive 2x squared. Let's see, that's going to be 12. Positive 12x. That's a positive 5. Positive 10. X plus 3 cubed. I end up with this 2 negative 6's cancels with that 12. Negative 8 over x plus 3. This is a wonderful problem. Hint, hint. When will negative 8 over x plus 3 equal 0? Remember the rule. Your numerator divided by your denominator equal to 0 only happens when the numerator is equal to 0. Can you think of a time that negative 8 will ever be 0? And I don't know about you, but I can't. So there are no critical numbers from the second derivative. My brain's not working right now, but I'll say no points. That's it. No points of inflection. That means that we're not going to jump from one type of concavity to the other. We will have concave up, we will have concave down, but they will not connect. All right, so these are our critical numbers, negative 1, negative 5. It's also important to remember our vertical asymptote, which was at negative 3. And I think that's everything. We're going to go right to the graph, or not to the graph, I'm sorry, to the table. The table starts with interval. Then we pick a test value. We're going to analyze our first derivative, make a conclusion. I write C1 because it's the conclusion from the first derivative. We're a little fuzzy right now. Focusing my adjustment here. Oh, my manual focus was turned off. There we go. Then we're going to figure out the second derivative and make conclusions from there. My interval had no other restrictions than these three numbers. I was not told that we started from a specific point and ended at a specific point, so I'm starting at negative infinity. That is the most to the left that we can go. I'm disrupted at negative 5. Then I'm going to go from negative 5 to negative 3, negative 3 to negative 1, and negative 1 to infinity. Test value just means pick a number from each of those intervals. It does not matter what that number is. You could pick, like here, negative pi. It wouldn't matter. And first derivative. Now let me remind you of what the derivatives look like. This one was negative x squared minus 6x minus 5 over x plus 3 squared. We also saw it as negative x plus 1, x plus 5 over x plus 3 squared. The second derivative is equal to negative 8 over x plus 3 cubed. Here's all I do when I'm figuring out my first and second derivatives and making conclusions. I plug in negative 10. I'm going to plug it in here. Negative 10 plugged in here would give me a negative number, another negative number, and it would have a negative in front. So 3 negatives make a negative. Anything squared is a positive. A negative over a positive is a negative. I don't care what the number is, I just care about its sign. -4. We're going to have a negative, we're going to have a negative, we're going to have a positive. Negative, negative, positive makes positive over positive. -2. That's going to be negative, that's going to be negative, that's going to be positive. Negative, negative, positive is a positive over a positive. And 0 plugged in will give me a negative, positive, positive, which is negative, over a positive. Okay? My second derivative, when I plug in a number in the denominator, and that number's -10, this becomes negative. Cubing it remains negative, so negative over a negative, if you want to write it, negative over a negative is going to be positive. Over here, if I plug in -4, the top is negative, the bottom will be negative. If I plug in -2, that's a negative, this will be a positive. And if I plug in 0, I'm going to get a negative. Alright, so you're going to see me use just some arrows, but those arrows have very different meanings. I'm making arrows go up for everything that's positive, and I'm making arrows go down for everything that's negative. But those arrows mean something different. This arrow means decreasing, this arrow means increasing. This arrow means concave up, this arrow means concave down. There's also 3 points that I need to consider. Actually, I take that back, there's more than that. I need to know what happens at the point -5 something. I need to know what happens at the point -3 something. I need to know what happens at the point -1 something. And if I had endpoints, I would want to figure out those points too in order to talk about extrema. These numbers are found in the original function. The original function was -x² minus 4x minus 7 over x plus 3. If I plug in -5, and I'm going to cheat here just for time's sake, -5 squared minus 4 times -5 minus 7 all over -5 plus 3 is 6. Let me cheat this time. -3 can't divide by 0. I saw that coming, so I'm just going to do that. And then if I plug in -1, that comes out to be -2. Alright, so here's what I see happening. As I graph this, you're going to see it a little bit better, and I'll reference those points here in a minute. I do not have a straight edge. What can I use next to me? What can I use? I have a piece of paper right here. So you have no excuses at home. If you don't have a ruler, you can always use anything that's straight. So I'm going to eyeball where I think the middle is, right about here. Remember, always label X and Y. Alrighty. I'm going to draw the points that we found to be significant. Points like -5, 6. -1, -2. We also had an asymptote at -3. X equals -3, so I'm going to draw that in. Not only am I going to draw it in, but I'm going to label it. We had an oblique asymptote at the equation y equals negative x minus 1. So right here, and then with a negative 1 slope. Oblique, diagonal. You have to go tell Mrs. Welsh that you did oblique asymptotes. I know she covers that in pre-calc. Notice too that I labeled it. Always label, always, always, always. I also had a y-intercept at, if I remember correctly, negative 7/3. So that's negative 2 1/3. I'm eyeballing it right here. All right, now what else do I know? I know that from negative infinity to negative 5, I have a graph that's decreasing and concave up. What would it look like to be decreasing to this point but be opening upward at that point? Well, hopefully you see this right here. Now, why did I go up on that side? Because on the other side, it's increasing while still being concave up. So this all flows together. There's no issue here. There's an issue here because of the asymptote. Everything else should be continuous over here. On the other hand, we have a continuous function that's increasing then decreasing, but it's concave down. What would it mean to be increasing and then decreasing from this point? Increasing to the point and decreasing down from the point. But notice that we have this oblique asymptote, so I want to ride real close to that. This is my final response for my graph drawn. And then it's not until this point that I'm going to check with my calculator. Negative x squared minus 4x minus 7 all over x plus 3. Does that look like the graph that we have? And the answer would be yes. That looks pretty close. All right, and I'm going to stop this here because this question right here is the one that most closely resembles the one on your test, so I'm not even going to review the other ones. I'm going to let Ms. Ollie do that in class.